tomorrow or tomorrow morning 1 hour I'll try to cover the clustering. Okay, so I hope you're all clear about what is classification, how we do a decision tree, right? So there is the last part which I wanted to cover and then end the session. Okay, so just go with this PPT and go with the code, which I already shared that coding for the for the decision tree code. With this, both the decision tree code is already shared. I'll be sharing you the PPT. So with that, you should be able to understand. And this is already shared with you. That statistics code, whatever I explained you today, is already shared with you. The only pending part is clustering. That we will cover tomorrow. Another 5-10 minutes, I will take it about the metrics, which is very important metrics. I'm trying to confuse you. Hopefully, you won't get confused. If you don't get confused, that is good. Then we'll have a session. I'll hand over the session to Mr. Ranga, so he will carry forward, right? So in the here, see, we have done one decision tree, right? Basically, no matter what, you work with any method. Whatever I'm teaching you is going to be applicable. Are you seeing my screen? Madam?
No. We are only seeing you.
Oh, yeah. Okay. Yeah. Okay, I'll share the screen now. Are you seeing it now?
Yeah.
Great. So there are many parameters available. So we're talking about so many methods, right? Even in the normalization itself, you have so many methods, right? And when you're talking about distance calculations, you have so many methods, right? And when you're talking about classification, there are so many algorithms. You're talking about clustering, there are so many algorithms, right? When you're talking about text mining, there are so many algorithms. Neural network, there are so many techniques and algorithms. So there are plenty of algorithms and plenty of techniques, right? And we have applied everything through machine learning. So basically, we have handed over the model, whatever human thinks, the human model. How you, for example, how you find one student is a good student or bad student. How you predict one person is a good fit for the for the future CEO or future CTO. Like you apply your brain, right? So based on that, you build some expert system, you build some model, etc. Right? With all, we wanted to find out how accurate that is. Right, so accuracy plays a very, very important role in any algorithms. This is very important, like precision, recall, accuracy, confusion matrix, and F-score. Because, for example, there is a COVID test. Sorry to use a COVID-19 test. Right, COVID-19 test predicted, the machine with the test and all those things predicted it is positive, but actually, doctor came. And this is basically based on the lab test, based on some automation, based on some blood sample, based on some reference of data. A lot of references given. With all the references are being thrown, they apply to one tool. Okay, COVID prediction tool. Okay, COVID predict tool. The tool has predicted that the person X is positive, COVID positive, whatever, right? But when the doctor analyzed and then checked the real pulses and fever, he doesn't have any problem. He doesn't have any fever. He doesn't have the symptoms and all. So doctor is saying that no, he is ex-COVID. He's a ex-person. He's not. He's a COVID negative. He's not a COVID infected patient. He can free to go. So there is a confusion here, right? Basically, predicted versus actual. Are you clear what I'm trying to tell you? So there is going to be a confusion, predicted versus actual, because machine is predicting something, actually what is that happening? That will bring down to a confusion metric. So we always have to do performance evaluation. If you are working with the computer science, you know there is something called data structure. We always look at data structure in terms of complexity, right? So there is something called time complexity, very important. and then space complexity, right? It's very simple. Basically, how much times, steps, iteration it is going to take, n square, n power 3, whatever, and then how much space, right, the storage wise it is going to take. So if this is going to be so high, then you don't choose algorithm. There are so many evaluation parameters are available which can check the performance. I'll show you one comparison later on. That iris code I have, I'll show that. So that is basically where we are getting. How do you find the performance of the given method? How you are sure, how much you are sure that the given predicted answers are close to the actual or real-time answer. Can you believe the machine? That is the performance measures what we are talking, right? So confusion metrics. See this? Seeing my screen? See, confusion metrics says that. Can somebody says yes or no? I didn't see any of the chat. I'm only on the screen.
Yes, sir. Yes. Yes.
Yes, sir.
Thank you, brother. Thank you, sir.
Your beautiful face is also visible.
Oh, really? Oh my God, let me put the video off. Okay, fine. Okay, predicted versus actual. So there is again coming to the false and true. Okay, the for example, I tested something. Actually, it is false. Okay, actually it is false, right? What is predicted? So basically there are two results, negative and positive. You're all very clear. Okay, true negative means basically the predicted result, okay, predicted as negative. For let me put it this way, I'll go to the table, then only I'll understand. Okay, for example, doctor says you are COVID patient, you are COVID infected. Okay, right? But it is true. It is true. Actually, it is actual. Actual is true, but machine says you are not COVID infected. Okay, so this is called true negative. Okay, because we are giving the wrong answer. Okay, and whereas now doctor says you are COVID you are not COVID infected. False, right? And machine says you are COVID positive, right? So that's basically we are looking at it. True negative. If the result is really true, okay, what is actual versus predicted? Is it yielding to negative?
Just one small
Yeah.
point here.
Yeah.
Okay, true negative, true. Okay, fine. Okay, you're saying a false actual. Okay, once you complete, I won't ask a question before we move to the next slide.
Sure. So basically, we wanted actual to be true, predicted to be true. We want more true positive. That means whatever I am predicting and actual supposed to be true. This is a good condition. So actual and predicted should be true negative. Suppose like say this is also the doctor also predicting it as a negative and machine is also predicting as negative. So this is good. True negative and true positive is good. Okay, both true. But actually it is false. But actually it is how do we put it this way? So here this is basically false positive, right? False positive means predicted is false positive. Predicted is false positive, right? And here if you say this predicted is false, actual is false negative. Okay, so that is what basically actually you have true, but the machine predicted as false. So that's why it is called false negative. Actually we predicted it is false, but the machine predicted as true. So there is a confusion. That is why it is called confusion matrix. Okay, let's see some more, then you understand.
One second, I want to just ask one question to the participants. Of this four, which is more dangerous? Which is the one that you should not do? Your algorithm should not do. I'm getting mixed answers. That's why I asked this question, doctor. You got 4 different answers.
They have got confused.
Don't worry, just think and answer. No rush, because that's why it's called confusion matrix. Like doctor, please. False.
With some example I will give, no, then they will understand more.
Okay. That's
Yeah.
correct, sir. Bingo.
What is answer? False, positive, false, negative. What did they say?
Yes, Revati madam, கோச்சிக்காதீங்க சொன்னீங்க. ஆமா.
Predicted, what did they say?
False negative. False
Exactly.
negative.
Exactly. Perfectly
A lot
correct.
of them said false negative. A lot of them said.
Excellent. Okay. Now you see
Explain
this.
them why. Explain them why.
Yeah. So when do you get precision? I get all true positive. The machine is predicted true positive and actual results with the actual result. Actual results mixture of both the true positive and false positive. Suppose the true positives are more, we are finding more precision. That means the machine prediction is much better. Our precision is better. The machine is thinking fast. Machine is doing the correct work, right? And if I have this recall, okay, so where we have true positive by predicted results, right? So would we be able to recall? Is it machine is giving the correct prediction with respect to the actual? So here we are comparing with the actual. The prediction is for actual versus the true positive. Out of true, and how many true positives we have found? There are some false positives also there. How much we got? But in the recall, in the predicted results, how the machine algorithm is consistently working. Is it giving more positive, true positive? This is for, like, in the data mining, there's something called support and confidence. So this is the basic support. This is for a confident of the method. So this will gives the precision. Yes, the results which I am getting it from my method is precise. And all my methods, every time when it runs, the recall, and I'm getting good true positive. Every time it runs, I'm getting true positives, right? Accuracy is basically true positive plus true negative. We want true positive, we want true negative, right? So when a machine is predicted correctly, and actual is also correct. So if it is a true, means true. Either COVID true, machine is also predicting COVID true, actually it's also COVID true. Machine is predicting negative, and actual also predicting true negative. This is okay. So true positive plus true negative divided by total is called accuracy. Okay. So F score is nothing but 2 times F score or F1 score, 2 times precision into recall divided by precision plus recall. I'll show you an example and then I'll wrap up my session. See this? Actual class versus predicted class. Cancer is yes. It predicted. Okay. So here we got 90, 210, okay, and then 140, 9560. So what you have to do is like a row total, column total. So basically, if you look at it here, this 90 plus 140 is 230, 90 plus 210 is 300. Row total, again, this is row total, and this is column total. So if you look at this, accuracy is 96.40, right? So accuracy of the proposed method compared with the actual class is on the left, this side, predicted class on the right side. So suppose what it is says, I'll explain you this data. Out of 230 cancer yes, okay, out of 230 cancer yes for actual predicted, 230 predicted cases, the true cancer yes was 90 and no was 140. Okay, again when it comes to the 9770 patients of cancer no, so see, this is good. 9560 out of 9770, this no and that no is matching. Okay, so that is basically we are getting good accuracy, 96.40, because actually we are predicting as cancer is no, and the machine machine prediction is also, closure. Out of 9770, out of total of 9770 sample, we have only deviation of 210, so which is okay. So we got about 96.40 accuracy. Okay, so this is with that I'll end this code, and I have shared one Iris code. What normally machine learning algorithm will do is you have to. I think I have the Iris code here. Yeah. So you don't have to worry about it. There are metrics available. See this are you seeing this from sklearn metrics import confusion matrix? You just import this confusion matrix. It will automatically brings the confusion matrix for you. You can print the confusion matrix. You can print the precision accuracy. See this? It is printing the confusion matrix and it is printing the accuracy score. See this? I'm printing the accuracy score. The model, what model which is predicted based on the given data validation, it says 96% accuracy. Okay, so this code also will, I don't know whether I shared this code or not, but I'll share this code with all of you through, or I'll share it in the email. Okay, so with that, I'll hand over the session to Mr. Ranga. So its floor is all yours. Go ahead. Thank you.
Thank you, Doctor. Can you stop presenting, please? Hi, good afternoon, everybody. Just confirm whether am I audible?
Yes, Mr. Ranga.
Yeah, perfect. Thanks, Doctor, for the wonderful sessions. It was very good. Hopefully, I'll be able to keep up the same pace and keep the audience engaged. God bless us. Okay. So is my PPT visible, right? Is it? Okay, I think I have to go there. Before that, I'll be just
Pin. No.
Myself. Okay, I'm not able to pin myself.
Now you go to your people, and then you see two will be there. No, one on your wall, the other one you try to pin.
Okay, got it. Okay, is the PPT visible now? I'll just make it
Yes,
full presentation.
coming up.
Okay. It's visible, right?
Yeah.
I think. Okay, perfect. So basically, I think somebody has to mute. I'm hearing myself again. So we're going to talk today about, somebody has got it on speaker, I think, because I can hear myself. Okay, let me just check that. 1 second. I have to turn my video off. It's okay. Okay, good afternoon, everybody. So let's, we have been having wonderful 2.5 days with artificial intelligence and having a lot of fun. Yes, all of you are having a lot of fun, right? Yeah? Are you all ready and ready to go with the deep learning? We saw about the artificial intelligence. We dwelled into machine learning up to today. And now we're going to take you into this world of deep learning. So you crossed 2 layers already. Congratulations to all of you for making it this far. And now let's go into deep learning and try to understand what is deep learning is all about and how does it help the existing systems and how does it help the AI and its future. So this is a deep learning timeline. I'm not going to spend a whole lot of time here, just to show you that it is not new. It has started in 1940s. So it has gone all the way up to 2017 and 2020. So slowly things got introduced into the system, from back propagation to recurrent neural networks, LNets, long short-term memories, deep belief networks. Then this is a dropout. This is a regularization technique. Then capsule networks, deep Boltzmann machine, GANs. This is what I was telling, that you can train a computer to write novels for you. So that's where it's going on. Now we are actually moving over into something called as explainable AI, XAI. So one of the major problems of deep learning is it's always better to start with the the cons, because you just that gives you better understanding. The best thing is it does a lot of good things, and it is black box. Black box means it is hidden. It's quite a few things that you don't know how it comes across, how it is getting done. So the new feature that is being catching up is called as explainable AI, which writes auto MLs, and that is what is coming up. So we will cover that probably in the next session on where we are. So on the timeline again, it was in 1943 the first mathematical neural network came out. 65 was the first networking model. Then we had this NetTalk, which could pronounce the English words in 1985. In 1989, they had a system that could read your handwriting. 2009 was an ImageNet launch. We will see this tomorrow probably when we are talking about convolutional neural network. This is a very interesting topic. This gave birth to convolutional neural network. Because of this ImageNet competition, CNN came out. There's a very famous architecture called as AlexNet. There's also an architecture called as GoogleNet. Then came the CAT experiment conducted by the Google Brain. Eventually, Facebook developed a deep phase. We're going to see how this deep phase works today to identify the images. When you put your image picture on the Facebook, it immediately tells you to tag. How do you think it works? We're going to see it today. So it's going to be interesting, fun-filled session. So get ready, put on your seat belts. Let's go for a ride. Let it be a fast one. So this is the Neuron model was initially suggested by McCullough and Pitts, and then it slowly moved on. We are going to see in detail about perceptron, Rosenbahl's perceptron model, and we're going to then it slowly went on catching up from different inventions. We're going to be looking at the feed-forward network. We are going to be talking about max pooling tomorrow. We're going to be talking about ReLU. Data augmentation is decay, dropout, overlapping pooling are all very advanced topics. We're going to be talking about GPUs, and we're going to be telling you how you'll be able to get into the Google Colab. How do you go about doing it? And then we're going to be talking about CNN. This is the AlexNet that I was talking about on the CNN. So this is a basic flow. So basically, where did this start? Why did we go into deep learning? In 19th century, people started asking, can machines be intelligent one day? Then let's build an intelligent machine was in 1956. Wait, what is intelligence? Then they started asking that question, and then they figured they need to go deeper. That's where we are with the deep learning. So what is the difference? Sir, you're saying deep learning, he's saying machine learning. What are you talking about? Is there a difference? Can we, see it, or can you explain it? I'm explaining you with the same example. In machine learning, what were you doing? You were doing something called as feature extraction. Where were the features? We were saying features and observations, right? Where were the features? Doc, can you please tell me how they responded? Where were the features in machine learning? What were the features? Doc?
So no response still.
No response. Features.
Came inputs, data set, attributes, parameters.
Exactly, attributes. Very good. Attributes were the features. So today you are supplying to the decision tree a whole bunch of features, and then it is deciding whether it is hot or cold, whether it is sunny, right? So you give a car and you sit down and you extract the information about this is the car, this is how it looks, it's got 2 tires, and then you send it through the classification model using decision tree or nearest neighbors, Naives Bayes, you know, name it, market basket analysis, anything. Then it decides whether it's car or not a car. That will be your output. Here, deep learning, what is missing? This feature extraction part is not required. I don't have to sit down and extract the features. My system will automatically extract the features and tell me whether it is a car or not. I'm talking this, it's a very, very base level, okay? A very base level. My neural network, this is called as the neural network. My neural network will study this, understand the features, build its own feature set, and say, hey, I think it's a car. It's not a car. Okay, that is the major difference. So this feature extraction part has been dropped off in deep learning and it has been taken over. So this way, I can show anything. So you might ask one question: how will it know, sir, whether it is a car or a bike? That is where training comes in. So how do you know it was a car? Somebody taught you, right? This is the car, this is Mercedes-Benz, this is BMW, this is Fiat, this is Ambassador. How are you able? You are seeing, the more and more you see, the more and more you train, the more and more you learn. That is exactly true. Very simple. As again, doctor will make fun of me, but computer science is common sense. So whatever we do is what we want the computers to do as well. So more you show them different types of cars, then again you show another BMW, it will say first it's a car, and then it will further classify that as a BMW or a Mercedes-Benz. Okay, so how are they doing this? The inspiration for this came from the human brain. So now we're going to become real medical doctors now. So this is how the outlay of a brain is. So there is dendrous cell body, then it sends the signal out. This works on the signal and then you react. So something happens, you touch a hot water, immediately says it's hot. It sends a signal, an activation function to ask you to take your hands off. That's what you're going to do to your computer now. There are 100 billion neurons, around 1,000 connections. Electrical signals are transmitted through axon and can be inhibitory and excitatory. Activation of neurons depends on the inputs. We are going to do all this exactly. I'll show you in the next slide. See, one-on-one mapping. I'm going to give inputs. This is my nucleus. It's going to work on it and it's going to give output. So does it look exactly like this? The dendrites, the sensory organs are your inputs. Then you have your brain, which is a neuron, which is going to have a integration function and an activation function. And that activation function will decide what to output, and it will output and give the expected results. Are you with us so far? Doctor, are you there?
Yes, Ranga, I'm there.
Yeah, here's your human brain frequency. Go ahead.
Okay, sure.
Somebody was asking about this morning. Doctor is very good at explaining this. I let him do it.
Oh, really? Oh, my goodness. I'll give it a try. Yeah, let's keep that.
You didn't know that you were good.
Oh, really? Okay, I'll try. So basically, you are going normally. Suppose somebody is coming and then trying to hit on your face, or there are like our brain works based on different things. Suppose right now I'm working. All suddenly now Ranganath called me, right? So just got that thinking, situational, right? So alert, engaged in work, busy thinking. I was doing something, then doctor, are you there? Okay, then alert mechanism, right? So basically that happens during the normal working hours. So this is basically what we are actually dealing with, beta. So it basically all these signals, EEG, all the EEG signals, our brain signals. So Ranga, I would like to show one brain machine interface diagram to them so that they can understand. Yeah, excellent. So there is one more diagram for the brain. So you all know like a EEG signal. Just show the EEG.
This is the EEG signal.
Yeah, correct. So basically what they do is how our brain, there are a lot of parts in the brain component. I don't want to go so much into the anatomy part, but when you look at it, there are some sensory organs that takes it and then transform everything into a form of a signal. And every signal will work with some level of frequency, right? So if you see that, we call it...
The frequencies that you're talking about is here. What doctor is talking about is right here.
Exactly, the beta rhythm.
30 hertz, 9 to 13 hertz.
Exactly. So like say, we talk about when I am singing in orchestras with multiple people, they'll give a chord, okay, C major, C minor. So I have to go into that pitch, okay. So any signals which comes within that range of 14 hertz to 30 hertz are all mostly towards alert, normal working hours. Like say 9 to 5, 9 to 6. Okay, suppose now after like 5 o'clock, I'm just relaxing it and watching TV or doing some, looking at the news and things like that. Our mind is kind of relaxed. That will be the alpha rhythm. That's why there is alpha yoga, alpha mind yoga. Let us relax your mind. You go, there is alpha. I think somebody is laughing, smiling. Sambada Bulavani is smiling, I think. Okay, now relax your mind, So that's where this alpha will come, right? When you are going for theta, so wherein you are going to some state like sleeping state, right? And you're going to deep meditation state. Ranga is showing that, right? Between awake and sleep, wherein you are getting the creativity. For example, when I'm going to sleep, I will have some thought process stating that, tomorrow I have to do this, or I'll chant something, right? So that will start, there are some thought process will go. Basically, in your subconscious mind, it's not unconscious. So these two are conscious. So the first one is regular conscious. This is somewhat relaxed conscious. Third one is almost your subconscious mind start thinking and giving some inputs to you based on what inputs you have put in. Like neuron, he's talking about neuron, right? So based on that, like say, there are a lot of creativity ideas will go. That is where the theta plays a more role, okay? And then go to the delta. That basically still, it's a very deep sleep or unconscious. So we are not going so much into delta. Most of the EEG signals, in fact, when I was presenting about, there's one session we can have a brain-machine interface, how brain works, how machine works. In fact, you get a chance, you look at some of the videos. There was a proof that one person doesn't have the right hand. Okay, artificial, they replace this right hand for one person, and they used another person's brain. Another person's brain transform that signal to this person which doesn't have the hand. They transform the signal so his brain doesn't think. Madam, somebody is Kalai, please put on mute, ma'am. Dreams will come under beta or something else. Okay.
Thanks, doctor. Thank you.
That's a daydream. That's a daydream. Yeah, daydream. Yeah. Sometimes.
Thank you. Thank you. You can start dreaming now.
Yeah. So you can make that signal transfer to the through EEG. So this brain, the brain, they have some brain. Their brain doesn't think. Okay, they're kind of having some diseases or brain dump or whatever. So, but they wanted to move the right hand to hold something. They did the programming from other brain. That other brain say, raise your right hand. That artificial organ used, and then it was raised. Similarly, the left hand. So the machine to machine, brain to brain, they have done the control. How it is possible? Because of this alpha and beta, right? So what we are trying to do is the neurons, there are mappings available inside the neural network coding. That's how they've written. They take any frequency. Ranga taught you about the fuzzy, right? So which one is it? Between 14 will be the lowest value, 30 will be the highest value. They will try to take all the the frequencies within that range and trying to control what you need to control. So suppose in the factory, the normal hours, what human being do. Actually, Amazon does this. Amazon uses beta rhythms. For example, I'll ask Jyoti Munch or Dr. K. Dhanlakshmi. Dr. K. Dhanlakshmi, you start testing the students, giving a quiz or test. You will do that. What you will do, madam? Madam, you can speak, unmute and speak. Suppose you're taking one subject. Dr. K. Dhanlakshmi, ma'am, are you there? Ma'am? Okay, I'll go to Parvati Ankadi. Someone. Okay, I will go with the other person. Anybody else? I can just go who's ready. Okay, I will go with Revati ma'am.
Good. Good
Revati
choice.
ma'am.
Very good choice, sir.
Sir, tell me again, sir. I did
Okay.
ask
No
a question.
problem.
Yes, sir.
So now you are the relaxed.
Revati madam was in theta state.
Okay.
So tell, yes, sir.
Revati ma'am, what subject you are teaching, ma'am?
Information theory and coding, and one more is digital communication, sir.
Excellent. Now you have to give a test to the student. Test
Okay,
to the
sir.
student. Quiz. What do you do? What is the way you do? Tell me.
Sir, with respect to COVID-19 situation, I want to explain or else normal.
Normal. Don't worry with COVID. Normally, no pre-COVID.
Okay, sir. Normally, I will make them to actually like Q only. I will handle my class, sir. Normally, I will say questions and ask them to. I will get explanation from the answer. That's all, sir. I can do
ma'am.
two-way
No.
communication.
No, you simply
Normally,
go. No. Let me ask you the question. You're directly going to go out and then start writing. Do you think that the student will understand? They have.
no. First, I will check. I will recap the previous class and I will call questions from that same,
Okay.
sir.
So basically, you will give some alert. Okay.
Yes, sir. Yes, sir.
Right. Hey guys, girls, students. Today, in another few minutes, we are going to have a quiz, and this is what it is. Like 1, 2, 3, 4, 5. You intimate, right? That's what happening in the data, because students thinking will be something, because even machine is also the same thing. Machine also simulate the human, right? So when you suppose the machine is going to give the quiz, same thing is going to happen to machine also. Machine also will be doing something else. So we will try to have this beta rhythm and give the instructions and then make it start becoming active. Then you start getting into the other rhythms to configure. I think Ranga, it should be enough. I think you can go.
Yes. Thank you, doctor.
You're
Thank you
welcome.
very much.
Yeah.
Fantastic explanation. So let's move on. So this is similar to what the doctor was speaking, how the human brain machine mapping happens. There is a trigger and the EEG recorder will go ahead, try to do a pre-processing, will extract the feature and start classifying. So this is exactly what the neural network and the deep learning CNN, RNNs will follow.
Yeah, well, Ranga, sorry, go back. I'll tell you one example also. See, machine does not understand few things, okay? Like say, like we say, like, okare, kundiko, abdinna, we will sit. Aram say, chukkaro, or whatever you say in Hindi or Tamil, we will understand. Hey, pasangala, satam bodadinga, don't shout. Like that you can tell. But machine doesn't understand that. So that's why, okay, now your mind is saying that you are going to give the quiz to them. Revati ma'am will say, guys, please be quiet. You will tell that, right? Then when they say the word please be quiet, that means the students have to be quiet. So that is the English letters and words. So that's what Ranga is showing. Basically, it takes that signal for like now be ready. There will be a signal, be ready. That means the machine will see that be ready, be attentive. That words, the number, be ready at 2 p.m. That's what Ranga is showing. Ranga, show that diagram there, A letters, yeah. So Be ready. There is B there. E is there. Take that. R is there. Ready there. Be ready to take 10 items. The number 1 and 0 will be taken. That is the inputs which reads, sends it by looking at the instructions given in the BCI interface. Okay, so that's how it takes it and then gets to a feedback, and then now it will ask, like Ranga told on day before yesterday, machine podu, TV podu, put the TV down means you just put the TV down. Okay, so it will classify what type of instruction is that. Load 10, where I should load. Okay, where should I load it, here or there? That is where that feature extraction and pre-processing happens, and then classify accordingly. The machine will start mapping the work. Excellent. That's all. Thanks, Ranga.
Thank you. Thank you. So this is a simple one-on-one mapping where we have input layers, hidden layers, and the output layer. This is similarly where the circles are about our neurons and the arrows are the synapse. See this, the synapse is the arrows and the weight is the electric signal. So just now, doctor explained to you about those signals. That is the weight that is going to go on this signal. So you please vision this. If you vision this very clearly, you will enjoy the rest of the slides and the class. So whenever you see a circle, that is a neuron. Whenever I see your arrow, it says that is the nerve that carries your signal. What signal, whether it is theta, three key things you're going to see. Okay. One other thing, important thing about deep learning is the output. The neural network learns complicated structured data with non-linear activation functions. The difference between linear and non-linear activation is there's got to be no correlation. It has to be different. So then only you'll be able to identify a car from an aeroplane. So how does the neural networks learn? I'm showing a picture. How does it start? Somebody is on unmute. Please mute yourself. How does it start learning? Because I said here, it's going to automatically extract the features. How does it extract the features is what we are showing here. It works on something called as compositionality of data. Composition. What is composition? Music composition. You're writing a composition. You put bits and pieces of music, and at the end, the music director will combine all that and give you a music. You're writing a composition. You start with the introduction, you write the main body, you write a conclusion. Of all the three, when you put together one by one and you read it, you finally end up with a final product. That's exactly has been lifted out there and put right here for you. Layer 1, algorithm first learns to recognize the pixels and then the edges and the shapes. So when you show a face, it comes and sees, watch my mouse pointer. It just tries to learn the edges first. Okay. So because now if I come and I'll try this. If you see something like this, if you only see this outline, what can you say? Okay, and this says that is. Let's assume this is water. Okay.
Looks like a mountain for me.
It looks like a mountain for you, and this
house
looks like a house, right? Because you are able to identify this just from the outline.
Somebody saying that.
Hut. Yeah, perfect. So I didn't tell you this is a house, this, because the outline is showing you this looks like a mountain, this looks like a waterfall, just with the edges. Just with the edges you are identifying. That's how the humans identify.
One thing, Ranga, to add, see, this is where the reasoning will come into picture. We are already fed with the known factor, the knowledge. We are already fed the knowledge that this type of things, like say, previous slide Ranga shown about the car. When the moment you see the car, you will identify as a car. How you are identifying always as a car? Because you from the childhood you have seen the car. What did you know? Car means it has a 4 wheel, and there will be an engine, there will be a mirror and things like that. There will be two mirror on the left and right, and it will make some noise and things like that. Bike means, you know, it is two, right? Like that. This is all being programmed and code, like a shape of the things and edges where the car end, right? The tail, when you know the car is end, the number plate is the end of the car, and the back number plate is the end of the car, right? Nobody put the number plate in the side or something like that. So there are some boundaries and things like that being given, so that, you know, by looking, but the moment you saw like what's the name? Somebody was saying about Hut. Who is that person? So I forgot his name. Yeah, Dachamapalli Sangamesh says that Hut. I was telling as a house. How? Because that's how I register in my mind. That's where the reasoning applies. The neuron takes advantage of it. That's what Ranga is trying to tell. Go ahead, Ranga.
Yeah, thanks. So once you learn from that, then you will move on and try to find out the complex shapes, like the, you know, the nose, eyes, you know, lips, and then on the layer 3, it learns which shapes and objects can be used to identify the face. So these are all layers. Again, it's another keyword that you need to register and take notes on. Neurons, weights, okay, layers. So these are all the words that's going to be used a lot in deep learning. So it's another picture. So when you come here, you show a whole bunch of pictures, the edges, tries to recognize the parts, and then see everything is an activation function. Moves to another layer, other. You can put how many ever layers you want. You will see this. Okay, again, one more, so that this is reinforcement learning for all of us. Successive model layers learn deeper intermediate responses. Layer 1, it recognizes this, combines form of objects and gives you a high-level linguistic representation. Okay, this is the technique that is being right now used in all the Facebook and social media. Whenever you post a picture, it immediately figures out and says and goes and checks the database. Hey, you can go take a picture with Arnold Schwarzenegger and post it on Facebook. Immediately it will say, tag Arnold Schwarzenegger. You are taking pictures with your friends. That friend's picture is already in Facebook. How many of you have noticed that you want to tag and you put your cursor there, it will say Venkat, Ranga. How many of you have seen that? Has it happened to you guys?
They're saying yes, Krishnakant.
Yeah, so this is exactly what, for others, they don't use Facebook, is it? Or they don't tag the friends.
Now, many have told us, many.
Perfect. Thank you, madam. So, how does it work? It works on this concept of 68 phase landmark estimation. This is used by Facebook, ladies and gentlemen. So, you see all these points here. It starts from 1, 2, 3, 4, 5, 6. It takes this point and see this. How beautiful. However your face may be, it doesn't matter. You could be slightly twisted like this, or you turned. Face area detected in the image. Then it will do the landmark. What it is doing? What did we explain? Edge. Edges. Captures the edges. The perfectly centered. Then it turns your picture. This guy is looking slightly the other side. It will take the edges and it will do a centering, and then it will do the face transformation and find it, who this person is, and ask you to tag. It's very interesting. Somebody has unmuted themselves. It's so beautiful. I can hear my own voice. I'm speaking okay. Thanks for the feedback. We're going to be using feedback in the deep neural network. Somebody already understood that and giving me a feedback of my own voice. Okay, how does this work? It uses a recursive checking and 68 landmark testing. Okay, the tool checks patterns by matching the testing images with other images of the same person and a new person. Then it encodes the correct image. After encoding, it searches the information like name, address, and then encoding and saves the image in that album, or it'll give you the name to tag. Okay. And one other thing, based on the edges, the compositionality will start figuring out the natural scene images. It sees this. Okay, this is grass. This is a whole bunch of people. This is a building. Okay, this is called semantic representation of feature segments. This is like a tree. This is like a building. It will start parsing all the images, natural scenes. We will see how CNN is used for tagging and all that stuff. Okay, this is the fun part. artificial neuron. Now I'm going to ask questions, you're going to answer. What this is the input, okay? In the brain, what picture we showed, what is this? The X1, X2, X3, what are those? In the brain picture I showed.
Dendrites, neurons.
Oh, they're saying okay, dendrites, okay. So
Yoga. Yoga is already in a deep yoga. So she,
yeah, Yogendra madam is good. She's
already creating more neurons.
Everybody madam would have answered. There's a whole bunch of Sangamesh. There's a whole bunch of about 20 people who are very active. I request all the others to be active as well, because we see 90 to 100 people, but we see about 20% responses. We want everybody to answer.
Prashant, Kulkarni,
please participate. Please participate. Don't be afraid. Don't be afraid. Give us the answers. Okay. So basically, the X1s are the inputs, and I'll tell you about this B later. The weights are your sensors, that the electric signal that comes. These are the weights. This comes to the neuron. The neuron has two parts. One is called summer or an integration function. Another one is called as an activation function. If you want, write it down. Inputs, weights, neuron has integration function, activation function. Then it gives the output. This is your artificial neuron. All these artificial neurons will also have an input called as bias. This B is nothing but whatever we saw yesterday in the linear regression, y is equal to mx plus c. Then we did y is equal to beta naught plus beta 1 x1, right? This is your beta naught in deep learning. This will always be 1. The value of beta bias is always 1. This will also have a weight input. Okay, that weight input also will come for the bias. So this will come in, and once this weight reaches a certain threshold, it will go and say, okay, if it reaches a certain threshold, which means simple mapping, I have enough information to take a decision, it means. So somebody is coming and touching you and asking, who am I, from behind. Will you be able to answer? You don't have a mirror. Somebody is coming and touching you and telling, hey, find out who's this.
One question has come from Jaya Pandian. Why using 1 for B?
That is like
Bias.
answer to that question is like A square plus B square formula, sir. That is what is they figured out is the best for the activation. Was figured by the scientists after research. They said using the bias as 1, because in one other explanation for that, even in your linear regression machine learning, once you find that beta naught will remain the same. Yesterday I did a calculation and showed you it's beta naught plus beta 1 x1. That beta naught is the coefficient that will not change regardless of the input that you give. You can have other variables that can change, so that's why it's constant. That's why B is equal to 1.
And one other thing I can add is, because it is both overfitting and underfitting, we wanted to make it
exactly. Bias is very good. Bias is also used to control your overfit and underfit.
Yeah,
correct. 100%. So when somebody comes and touches you, probably you'll be able to hear their voice, or you can ask something, say something before you can say who it is. So you can associate that to this. So when the inputs come in and the weights come in, and it reaches a certain activation integration value, then it will trigger. When it comes to this activation layer, there's a whole bunch of activation functions such as ReLU, TANH, leaky ReLU, sigmoid, softmax. We're going to see all that. So it will trigger that function and it will give you the output. So this is basically how this works. So when the artificial neuron takes this, how does it calculate this integration function? We're going to see that in detail. So when this is a simple neuron, okay, this is called as a single layer perceptron, SLP. It's only one perceptron. There are multiple layers. You can have MLP, multi-layered perceptrons. Then we have convolution neural networks. recurrent neural networks, and so on. So let's see how these weights are calculated and how things are working. So as I said, the building block of a neural network is artificial neurons. Okay, the neuron weights, what it is bias is always has the value of 1. So if you have two inputs, see, if you have two inputs, there will be two inputs plus one bias. You see, I have n number of inputs. I'll have n number of inputs plus one bias. Please follow this because I'll ask some questions. N number of inputs and one bias will go into this neuron. Okay, so the neuron will have two inputs and one bias, so it will require 3 weights. Okay, and one key thing you all have to remember is the weights that are given here are random. You will not, there are advanced technologies to control them, but for now you think you cannot control it. System will by default randomly assign weights. You just register that for now. Okay, but when we go into the advanced sessions, we will see how to control that. But for now, you don't know anything. I didn't say it, you didn't hear it. As far as you know, neural networks weights are assigned in a random fashion. So when the weights are assigned in the random fashion, what does it do? So what it does is it takes this input, multiplies by this weight, adds it up. x1 w1 plus x2 w2 plus x3 w3 da 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 da, xn wn plus b is always 1 into the weight will go here. See, the summation of 1 is equal to I equal to 1 to n xi into wi plus b. It just keeps coming. Okay, when it comes here, the activation function will look for the summed up weight input to output the neuron. So there is a threshold. I will tell this function, in this threshold function, I will say, hey, if it reaches a certain number, if these weights reach a certain number, trigger the output. So the output signal can go out once the threshold is reached. Say, for example, if I say, if the summed input is above 0.5, then the neuron will output value of 1.0, otherwise it will output a value of 0. So if it reaches 5, it will give 1, otherwise it will give 0. This is how the input output works. So a little, again, an explanation: 1, x1, x2, weights, net function, activation function, goes output. So this was designed by the researcher McCullough and Pitts. These two people designed this single layer perceptron. So please make a note. If somebody asks you who designed the single layer perceptron, you would be more than happy to tell them that this was designed by McCullough and Pitts. This architecture belongs to Rosenblatt's perceptron. He is the guy who created this style of perceptron and said, okay, it is working. So let's say step 1, initialization, b equal to 0, wi 0, I equal to 1 to n. For each training example, we will keep on doing this and we will trigger the output. This is a formulaic explanation of what we just said. So this is called as a sigmoid activation. If it is, the output is 1, then it is the exact output, otherwise it's 0. We will see this in detail. So this is a small example for us to understand. If I give the test score is equal to 7, grade equal to 6, bias equal to 1, the score will be 2 into test plus 1 into grades equal to 18. So if the score is greater than 0, you can accept. The score is less than 0, you can reject. So this is basically what a single layer perceptron is. Are you all with me so far? Before I go into the other advanced concepts, are you all clear about the neural network perceptron concept? If somebody asks you perceptron,
Yes,
can you guys tell me the different parts of the perceptron? Let's go. Shoot. Make us proud now. What does a perceptron have?
Input, they're saying, weights,
Okay.
bias.
Super. Then two other things, the important thing. What does the perceptron have? The main two things that is inside the
Activation. Activation function.
Which comes first? What is the first function?
IF input file. Input function. Wow. Summation, input function, threshold.
Summation, integration function triggers the output function. Activation.
Summation.
Very good, very good. What is the value of the bias?
1.
How is the summation done? If I have 3, okay, my question is, if I have 3 inputs, how many weights will be there? If I have x1, x2, x3, what will be the formula for the summation? Can somebody write it?
3 weights they are giving, 3 weights.
Yeah, 3 weights. Can you give me the formula? x1, x2, x3. What will be the formula?
3
like
plus.
Huh?
Okay. Yeah, I think I got it correctly now. Uma and Chandamir, Rajit Kumar says x1 w1 plus x2 w2 plus x3 w3 plus b.
Superb. Brilliant.
Very good.
Very good. That's
Good job.
it. So superb. Well done. Good job. Good job, all of you. So
I think, Ranga, if possible, what you can do is that computer prediction, no price. You can ask them, you can show them, probably they can, try to say like what would be the thing, or you wanted to go further and the end, maybe after the break we can show them.
Yeah, by the break you can say, you can load that on your screen and keep it ready. When they come back from the break, we will show them.
Excellent.
And we'll ask the question and then carry on.
Yeah,
Great.
sure. Yeah.
Okay. Super. So you guys are good now. You know what a neuron is, what is a perceptron. Okay, perfect. So let's move on to some of the little bit of a mathy concept, and I'm sure you professors will be ready. Keep your pen and paper ready. 3 o'clock is the tea break. So let's see whether we can catch up with the math before 3 o'clock. There is something called as gradient descent. I told you here, right? It's again coming back to the same y is equal to mx plus c. Okay. So gradient descent algorithm is supposed to find out the minimum. Here, the gradient descent is used to find the error. So we will go into detail a little later. So take a look at this. This is a global minima and global maxima. Here, I did the prediction. I gave an output. I did the calculation. I said it's a car. Now, what did we do yesterday? We used something called as RMSE. Okay, root mean square error. Now, doctor showed you confusion matrix. I actually wanted to tell you during the session itself, the confusion matrix and RMSE. RMSE is used if your output is continuous. Confusion matrix is used if your output is discrete. If you have to say how many patients have cancer or not, will he join the course or not, will he get a hike or not, those kind of situations you will be using confusion matrix. So once you have given an output, obviously these are all predictions. You need to check how far are we from the prediction, from the actuals. So you need to check whether your prediction was close enough or far away, and then based on that you should try to reduce the error. So let's say, for example, you have predicted your actual values here. Okay, local minima, meaning that the minimum error is here. Your prediction results coming out of your neuron is 4. Your job is to reduce. Your job is to reduce this error coming down. I want to come one step at a time and I want to reach here. That is your job. This is called as a gradient. Gradient means slope. Okay, this is the slope, right? This is the slope. This is called as a gradient. M is the gradient. I want this gradient to descend. I want my errors to come down. What we will see this. There's something called as a back propagation. I'm going to give you the program and we're going to work together. Madam has already shared the code. So please fire up your, I would request you to fire the spider. Keep your spider fired up. Okay. So this is what the gradient descent is all about. Okay. What is maxima and minima? Anybody has any knowledge about this maxima, minima? How many of you are aware of this maxima, minima, critical values, first order derivatives, second order derivatives? How many of you are familiar with this already? How's the response, sir?
Differentiate and equate to 0.
Super. How many, quite a few of you are already aware. That's it. Fantastic. So whoever is good in derivatives and linear algebra will love deep learning. That's your area. We won't see this math. Actually, you don't need to know this, but to understand the concepts, it's very important. Whoever is not, very savvy about it, don't be afraid. It's very easy actually. You will actually, I'll make you a derivative, a calculus specialist before the end of today, I promise. Keep your pen and paper ready.
Has given first order calculates min max and second derivative calculates the points.
Super. It's like a difference we'll see with the thing, but it's all correct, madam. Very good. Okay, so the maxima, don't bother about maxima now. We are only bothered about minima in deep learning, machine learning. Why we are only bothered about minima or minima? Can you guys give me throw some light? Can you enlighten me? Maybe I don't know. Maybe I'm saying something wrong. Why I'm saying I'm only interested in minima? Only descents. Why? What minimum? Why only minimum?
Minimizing the error.
Beautiful, sir. Who was that? Excellent answer. We want to minimize the error. What is the error in machine learning and deep learning? What is the error?
Reaching close to
Huh?
still coming.
We have to know this at least before we leave this.
Difference between predicted and actual value.
Fantastic. Thank you. Predictor. My dear friends, don't forget this. Don't go back and tell you attended 5-day FDP on AI, ML, DL, and if somebody asks you what is error, you should be able to tell them. Error and accuracy. Okay. You want low error, high accuracy. Okay. So if you're talking about minima, you're talking about reducing the errors. If you're talking about maxima, you're talking about more maximum accuracy. But we don't refer to that like that. We only talk about minimas. All the algorithms are bringing error down based. Even the optimizers, everything works like that. Okay, fantastic. So the minimum, so something like the minimum time to make a certain journey, the minimum cost of doing a task. Okay, so these are all the basic things that we are interested in. Functions between A and B. So see this picture, you will understand even much more better because you're all professors and doctors. Not like me, a normal engineering graduate. You guys are all experts. Like my doctor friend. Profit is equal to revenue minus expense. This can be represented like this. Profit equal is a function of revenue and expense. So if I say y is equal to f of x1, x2, which means f of x1, x2 is x1 minus x2. That is a profit. That is revenue minus profit. I'm bringing it back. So the optimum value of a function is f of x. So if f of x, if I say that is the optimum value of a function, and it is related to the change. The rate of change is called as the derivative, slope, descent, gradient. They're all different names too. So there is change in x, change in y, delta x, delta y, the slope of the line, y plus delta y minus y divided by x plus delta x minus x is delta y by delta x is equal to change in y by change in x. This is what we are looking at. How much has it changed? Okay. We'll assume with slope equal to 0 and we will calculate. Based on that, we will say whether that particular value is a maxima or a minima. If it is a minima, we take it. If it's a maxima, we proceed. So let's take this. Get your pen and paper ready. I'm going to give you a little problems and let's see whether you can. I'll tell you, explain this. The power rule. If n is any real number, d by dx of x of n is n of x into power of n minus 1. So if I write f of x is equal to x to the power of 4, I am bringing the 4 here. I'm bringing the 4 here okay? And then I'm doing n minus 1. So 4 to the power of 4x cube. 4x cube is my answer. So similarly, y is equal to x of 8 is, first order derivative of y is 8 comes here, 8 minus 1. So, okay, let's do this simple math. Give me 6x4. Oh, forget it. Okay, sorry. X to the power of 6. X to the power of 6. X to the power of 6. What is, give me the y factorial, y first order derivative. X to the power of 6. What is the answer? What is f of x? Answers are there?
Yeah, I'll call you. Yeah, I'll send you a mail. Sorry, Ranga, I was talking to madam. So Sudha ma'am. Okay,
No
done.
problem. Well, what is the answer they are giving f of x? For x to the power of 6.
6x power 5, 14.4.
No. X 6x power 5. Very good. Correct. Correct.
6x
Correct.
power 5.
So let's do x to the power of 9. I'm trying to write this with the mouse, so that's why it's like this. You don't have a pen. X to the power of 9 is 9x to the power of 8.
Correct.
Fantastic. Okay. Now we'll do a constant rule and a differentiable function. D by dx of constant u is, you will take the constant out and you will only differentiate the u part. So d by dx of c of x to the power of n, you're taking the c out, nx to the power of n minus 1. So if I want d by dx of 7x5, I am taking the 7 out, bringing this 5 here, and then n minus 1, 35x4. So give me an answer for 8x6. 8x to the power of 6. Eight x 6. Answers coming, doctor?
Yeah. 48 times, 48 into x power 5.
Super. That's it. Very good. Well done. So then this is the summation foundation rule. Similarly, you will be able to understand. If I write x to the power of 4, x to the power of 4 plus 12x, then f of x is 3x cube plus 12. Again, x to the power of 4 minus 2x, 2 plus 2 is 4 goes there, 4x cube minus 4 goes there, 2 goes here. So 2 into 2, 4, x to the power of 1. So the constant rule is 0. So this first order derivative is 4x cube minus 4x. Okay. So now let's try to find the slope of a equation with a tangent of the line on the curve 2 into 2x squared plus 1 at point 1, 3. So you do a derivative of this 2x squared plus 1, you will get 2 into 2x to the power of 1 minus plus 0, because 1 is constant 0, so you get 4x. I'm going to find at the slope 1, 3, where my here. So I'm trying to find out where it's cutting here. I'm just saying this is 1. Let's assume this is 1 and this is 3. Okay, so I'm going to try it at that slope. So m is equal to 4 into x is 1, right? The x-axis is 1. So probably this is 3 and this is 1. Sorry. 4 into 1. So now we have the slope at the tangent line at point 1, 3, and we can write the equation. So you start with the point of slope where y is equal to y minus 1 is equal to m of x minus x1. So y1 is 3 here, x1 is 1. So y minus 3 plus 4x minus 1, you multiply this and you end up with this equation, which is 4x minus 1. So that is the equation of the tangent line to the curve y of 2x squared plus 1 at point 1, 3. This is what we saw. Now we are going into this concept of finding the maxima and minima. If you can see here, ladies and gentlemen, which is maxima, which is minima, which graph is maxima, which graph is minima. The green one, red one. Please qualify green one. What is green one, maxima or minima? Red one, minima or maxima?
Red is minima, green is maxima.
Superb, superb. So you see this line here? Can all of you see the line? Let me show you. I have my thing working. See this point at where the line intersects. The x intersects your curve. That is called as a critical value. This is what is called as a critical value. So if you have given an equation, we will find out we have been given an equation and we are going to assume the slope equal to 0. If slope equal to 0, what kind of a line it is? If slope is equal to 0, what kind of a line is that?
Straight line, parallel line.
Fantastic. So what is the slope here? Why I am saying slope equal to 0, I need to assume here to understand the maximum and minimum derivatives. What is this?
0. Slope is 0.
Exactly.
Sambada Gulavani.
Too good.
Sambada Gulavani.
You guys are too good, man. So that's why I'm equating this to 0. Because I know y of minus x square is a critical value. I want to find the critical value for this and equate it to 0. Critical value happens only when slope is 0. So y is equal to minus x squared. I'm going to find out the critical value first, and then once I find the critical value, I'm going to find out whether that critical value is a minima or a maxima. This is basically, don't think too much. Just live the moment. Don't go, okay, we will see how it is used later. Okay. Y is equal to minus x squared. So how will you do the first order derivative? F of x is nothing but you bring your 2 here, 2x to the power of 2 minus 1 is 1. Minus 2x is equal to 0. When you equate this, what happens? X becomes 0, right? You take this others divided, it becomes 0. Then y is equal to x square. F of x, 2 of x is equal to 0. Again, x is equal to 0. So now we got a critical value of 0. Now I need to know whether this critical value is a minima or a maxima. For that, there are 2 ways to do it. You can do the first derivative test and figure it out, or you can do the second derivative test and do it. Let's see both ways. Using the first derivative test, I'm going to substitute 1 and minus 1 on this formula, f of x formula. So f of minus 1, right? I'm just taking this and applying to this formula. Okay, I'm taking my equation and applying that formula. F of minus 1 is, what is the formula? Minus 2x, right? I am applying minus 2 into minus 1. I got the value of 2, which is greater than 0. Then I'm taking this 1 and substituting in this formula. 1 minus 2 into 1, I'm getting minus 2. So if you take your value and substitute, and if your value goes from positive to negative, okay, when it goes from a positive to negative, then it is a maxima. I'm taking the same value coming here and I'm substituting this into another equation, this equation here, y is equal to x squared equation. Then I'm doing minus 1, 2 into minus 1 is minus 2, 2 into 1 is 2. So what is happening here? I'm moving from negative to positive. So this value is a minima. When I move from positive to negative, it's a maxima. When I move from a negative to a positive, it's a minima. So you decide based on these 2 tests whether that critical value that is cutting here is a maxima or a minima. This is the first order derivative. The second order derivative we will see, and then we'll probably take the break. Second order derivative is very simple. You apply the same first order derivative from the previous example. F of x is what? Minus 2x, right? We got this, right? So second order derivative is what? Again applying the derivative on this. X to the power of 1. So you're taking 1 here. 1 into minus 2 is 2. X to the power of 1 minus 1. X to the power of 0 is what? 1, right? So this is what is explained here. So I'll take a black pen.
Ranga, they want you to repeat that critical value thing. Deepika Sharma is requesting. Can you just repeat that? What is critical value?
This part, madam. Okay. Whenever your slope is 0, and when the line, the slope 0, when your curve touches that point, this particular point is the critical value. Okay. Once you get the critical value where slope is equal to 0, you need to find out, okay, whether that value is maximum or minimum. Here, if you take this, see this is the actual slope. So when the slope becomes 0, it's touching here. So we need to find, so it means that I have reached the bottom point or I reached the top point. See, if let's say I'm starting from here, I'll be going like this and I'm reached the top point. So the slope becomes 0. The line is flat. You see this, madam? If I'm starting from here, the error reducing, I'm coming here. I reached here. The line has become flat. Slope is equal to 0. Slope is equal to 0. I've reached a point where whether it is minima or a maxima. Now I need to know whether the region that I touched is minima, whether it is a minimum or a maximum. I need to know that. This far you're able to follow, all of you? Are they able to follow up to this point?
Yeah, I'm seeing yes, lot of yes.
Madam, the madam was the question able to understand that?
I think so. She says yes. Deepika Sharma said yes.
Okay, madam. So now you did that. Hold on to that slope equal to 0. Okay. Now come back here. So you have been given a equation like this. Y is equal to minus x squared. Let's say, for example, this is your value that has been given to you, and at that point is the value that's been given to you, and you figured out two critical values where it stops. See, it became 0 here. It could be anything. It could be 1/3 also, and this could be 2 also. Doesn't matter. I just took a small example. I'll show you another example in a PDF document. You'll understand more. Whatever value you get, okay, it doesn't have to be 0. So don't get confused because of that. Whatever value I get is the critical value. Now I need to find out whether my value touched here at the top or it touched at the bottom. How do I know? I need to do a first order derivative test. That's what I'm doing. When I'm doing the first order derivative test, I am just saying, okay, I'm assuming I'm going to substitute a value which is more or less same than the critical value. So let's say I stopped at this position. At this position is where 1, okay, and minus 1 it stopped. Okay, let's say my line stopped. That line stopped here. So I'm going to take this equation and substitute this. What is the formula for this? Minus 2x, right? So minus 2x. I'm just substituting here. I'm taking minus 1, minus 2 into minus 1 gives me 2. Then again I'm substituting 1 here. Minus 2 into 1 is giving me minus 2. When your value after substitution goes from a positive to negative, see here, positive to negative, then it is a maximum. So I can say, okay, this point which my program stopped is a maximum point. Here, if this condition is not true, I'm applying it on this formula and this is happening. It is moving from minus 2 to 1, which is telling me that the point that I've hit where the slope 0 is a minima. I kept on. See, what this program does is, you will see this batch gradient descent will do one come down. We'll check whether it has got the maximum or minimum. As it is the critical point, it will keep coming down, and until once it touches the slope 0, it will figure out whether it is a maximum or minimum. Understood, madam? Am I clear? You will understand even more when you look at the codes and the programs. It will take a little bit time to sink in.
Yeah, you can proceed.
Hmm?
Yeah, you can proceed.
Okay, so we'll just finish this and close. This is the second order derivative. Is I'm taking the first order derivative and applying again the same thing, 2 into 1. So here I'm getting a value of -2. Okay, so if you are using the second derivative test, if your output is negative, less than 0, then the critical value is a maxima. If it is greater than 0, then the critical value is a minimum. Okay, when you come back from the break, we can take a break. When you come back from the break, I'll show you this document. It's fantastic document, and you will be able to easily understand this in a much better way. This local maxima, minima, the saddle point I'll talk. So if this is an example, you're throwing a ball up in the air. How do you find whether it is the maximum point or the minimum point, right? You will see this, and then I'll again show you this with the slope. I was telling about the slope, right? Positive slope, negative slope, second derivative test. See, we will go through this example where -3.5 minus plus 1.3, 1 by 3. We will find out whether this is a local maxima or local minima. You see this? So I will show this. So we'll take a break, madam, and come back by 3.
One confirmation I want to have it. Sudha ma'am, I think, did you forward that Mr. Ranganath code? I think participants received that.
Yes, sir, already forwarded. Yes,
Yeah,
sir.
some participants, when you say Tanuja and other people, because Ranga, you're going to show that code, right?
Yes.
Yeah. So I hope all of you have received the code and the file. I think you sent Excel file also, right?
Yeah, Excel file also. I will tell Professor Vikas Dubey, I will tell the name to load, sir. I have sent like 3 different files. I'll tell the name of the file, you can load that file.
Yeah, and also whatever material we have shared today in the morning session, that is also shared. I think I've sent a mail to all members of the Python code of decision tree, as well as the decision tree PPT, which includes a confusion matrix and all whatever we have discussed, including the code for the Euclidean distance and the normalization. Whatever has been discussed, whatever we presented, it's all being shared. Hope you all received it. Good. Thanks for the confirmation. Ma'am, how much time we take a break?
3:15.
Till 3:15, sir.
Okay,
Thanks.
next 5 minutes, continue your break and then come back with the energy. And you have one nice, at the end of the day, like yesterday, you saw some, nice video. Similarly, today you'll have a nice video. That video make you very successful. Successful engineer, successful researcher, successful AI expert. So I'm waiting to show that after the break, and then maybe after Ranga finishes it. Oh, one person is asking a question.
That is on that confusion matrix.
Yeah, accuracy, sensitivity, specificity.
So others can take a break.
Yeah, directly proportional or not. Yeah, in a way, actually, if you look at the accuracy, just to give me a second, Ranganath, you probably can stop. I think your presentation is going like Anumar wall, Anumar tail. It is just going like millions of presentation. Thank you. Yeah. Okay, I will share one thing. Probably for the person Manjula is asking a question. So just I'm sharing that my screen. Sudha ma'am, I think you would have received that quiz 3, right?
Yes, sir. Yes, sir.
Good.
It will be posted by 3:30, sir.
No problem. No problem. I have for the participants, you have a mixture of questions on everything, neural network and whatever Mr. Ranga has covered, whatever I have covered, all be there. I think you will enjoy the question. Questions are also set in a different way. Hopefully, you will enjoy the question. Are you seeing my presentation?
Yeah, show them the formula. That's it, madam. Sensitivity, specificity, it's about those formulas.
Yeah. So if you look at it,
right, ROC
yeah.
curve. Yeah.
Specificity mainly address the true negative rate. So specificity, we look at specific. Sensitivity more related to true nature of true positives. And sensitivity is most related to true positive, sensitive, because I'm sensitive to comments and things like that, right? And whereas if we go specificity, we wanted to suppose I'm going to point out a mistake, specifically some mistake, right? That is basically we are going to tell. Clear, right? So this is not directly proportional. It is the specificity is proportional. The more of the negatives. Okay, then I wanted to specifically pointing down false positive versus the conditions, right? False alarm. Where exactly the problem have occurred. For that, we use that specificity, right? So see this selective true negative, and then you can apply false positive rate, right? So you refer this, and I would advise you to do little check, and then whenever you wanted, for example, I'll just show you imbalance data analysis. Yeah. See, perfect sensitivity and specificity of 100% each corresponds to respectively to perfect precision. No false positive and perfect recall, no false negatives. That's exactly what we are trying to do with that perfect sensitivity and specificity. So we are basically addressing the false positive and false negative. Hope that answers your question. Yes. Yes. I'm just sharing that. You can copy paste and also Wikipedia link, that will be helpful. Does it answer your question, madam? Madam, ketangla yaar ketangam theriyala.
Hello. Hello.
Manjula
Yes,
madam?
yes, sir. Sir, am I audible, sir?
Yes, ma. Purinjidamma, purinjidamma.
Yes, sir. Sir, the thing is, sir, your presentation and everything is good, sir. Nice for this kind of lecture first, sir. And here my question towards whenever accuracy is high, what about the nature of specificity and sensitivity, sir?
Correct,
It is to be high or some variations?
No, actually, again, you talk about the data, right? So
Yes, sir.
sampling, it's all about the sampling. How are you getting the true sample? When there are more true samples, which is more correlation, right? So
yes, sir.
Correct. And if there are, so sample is not so correct. That's why you studied in a type 1, type 2 error, right? So basically, shown here, here, if you see this on the specificity, which is mostly addressing the negative, true negative. Is it really, is it giving entire population? So that means your sample may not be correct. Your sample has to be increased, and or your sample has to be sized correctly. You understand, madam?
No response yet.
I think she.
Manjula madam, are you there? No, she left, I think.
Okay, no problem. So that me also, when I'm trying to say mute or something, I press that one button, then it just disconnected me. Okay, so that's good. I think 82 are still there. Good. That's good.
So are they following, madam, in that neural networks, neurons, perceptron? They're able to follow, right?
I'm seeing some
Yes,
there.
sir. Actually, the response is too good.
Super. So it's slightly a little advanced concept, but we want to
Yes,
cover.
sir.
It'll take a little bit of time to sink in. That's why I'm going a little slow.
Okay, sir. Okay, sir.